Welcome to Chemical Equilibrium, Lesson 4. Now we're going to talk about the Le Chatelier's principle. This is very important, especially for the shorter questions in your exam paper. Factors that can change the equilibrium position is concentration for reactants in solid or liquid phase, pressure for gaseous reactants, and temperature. This is very important for you to know. Factors that can change the equilibrium position is concentration, pressure, and temperature. So, when an external stress, that means if you have your reaction mixture and it is now at equilibrium, when something is done to that reaction to disturb the equilibrium, that is called an external stress. So now, when an external stress, for example concentration, pressure or temperature, is applied to a system in chemical equilibrium, the equilibrium will change in such a way as to reduce the effect of the stress. Now that is Le Chatelier's principle. Very important. When there is an external stress applied on the equilibrium will change in such a way to reduce the effect of the stress. So let's concentrate just on the concentration stress now. Here is a hypothetical reaction, and now the concentration of the reactant is increased. Then the equilibrium will shift in the direction of the reaction that uses the product to counteract the increased concentration. What that means is the equilibrium will then change to counteract the increased concentration of the reactant. So let's say the concentration of A was increased. Now you want to use A to get rid of it, and therefore more of the product will be formed. Equilibrium will shift in the direction of the reaction that uses the reactant to counteract the increased concentration. Like I just said, the forward reaction will be favored. If you add A, which is the reactant, you will want the reaction to use up A to get to equilibrium again. So if you add the concentration of the reactant, the forward reaction is favored. The same effect will be seen if the concentration of the product is decreased. That means if some of C is taken out of the reaction mixture, the reaction will want to make more of C to reinstate the equilibrium. If the concentration of the reactant is decreased, the equilibrium will shift in the direction of the reaction that uses the product to counteract the decreased concentration. That means if you want to decrease the reactant, you want to take away some of A. So now the reaction will react by making more of A to reinstate the equilibrium. So, if the concentration of the reactant is decreased, the reverse reaction is favored. That means more of A will be produced to reinstate the equilibrium. The same effect will happen if the concentration of the product is increased. When there is suddenly a lot more of C as a stress factor, then the reaction will want to get rid of all the C molecules to reinstate equilibrium as it was before. In summary, your forward reaction is favored when the concentration of the reactant is increased and when the concentration of the product is decreased. Your reverse reaction is favored when the concentration of the product is increased and when the concentration of the reactant is decreased. This is very important and will help you to solve questions. Let's do an example. For this chemical reaction, if the concentration of SO2 or the concentration of oxygen was increased, it will increase the rate of the forward reaction to get rid of that increase in the concentration. The equilibrium will shift to the right, and the new equilibrium will have more product than before because the forward reaction is favored. When the concentration of SO2 or the concentration of oxygen was decreased, you will increase the rate of the reverse reaction. The equilibrium will shift to the left, and at the new equilibrium, less product will be there than before. Very important. Now, when the concentration of SO3 is increased, this will cause an increase in the rate of the reverse reaction to get rid of that molecules of SO3. The equilibrium will shift to the left, and the new equilibrium will have less product than before. The concentration of SO3 was decreased. It would increase the rate of the forward reaction to make more of this SO3 molecules. The equilibrium will shift to the right, and the new equilibrium will have more product than before. The next factor that we're going to consider is pressure. When the pressure of the reaction is increased, that will affect the volume. So if you want to increase the pressure, you make the container smaller. Can you see that the pressure here would be lower than the pressure here? This will cause a high pressure because all of these molecules are bumping into one another and into the sides of the container. The equilibrium will shift to favor a decrease in pressure. If the pressure of the reaction is increased, how? By a decrease in volume, then the equilibrium will shift to favor a decrease in pressure. So when the pressure of the reaction is decreased, how? By a volume increase, increasing the size of the container, the equilibrium will shift to favor the increase in pressure. Example 1. For this reaction, the pressure was increased. Now, how will the equilibrium disturbance react? It would favor the reaction that decreased the number of gas molecules. Now, let's count the number of gas molecules. For the reactants, there are 3 hydrogen molecules and 1 nitrogen molecules. That gives you 4. For the products, there are 2 product molecules. So, to increase the rate of the forward reaction would then decrease the pressure which you want to reinstate equilibrium, and therefore the equilibrium will shift to the right hand side, to the side with the lesser amount of gaseous molecules. If the pressure was decreased, it would favor the reaction that increased the number of gas molecules, therefore the reverse reaction, because it will form more gaseous molecules and therefore increase the pressure. The equilibrium will therefore shift to the left hand side. Here's another example that you can go through by pausing. Then, the next factor that we're going to consider is temperature. Very important. An endothermic reaction uses energy or heat. So, delta H is bigger than 0, delta H is positive. For an exothermic reaction, heat is given off by the reaction. So delta H is smaller than 0, delta H is negative. This is very important. Now, when the equilibrium is disturbed by the temperature of the reaction being increased, the equilibrium will shift to favor the reaction that will reduce the temperature to counteract the change. The endothermic reaction will be favored because an endothermic reaction uses up heat, and therefore the reaction where delta H is bigger than 0 will be favored. When the temperature of the reaction is decreased and equilibrium therefore disturbed, the equilibrium will shift to favor the reaction that will increase the temperature to counteract the change. So an exothermic reaction is favored because an exothermic reaction gives off heat. Delta H is then smaller than 0. So in summary, if the temperature is increased, the endothermic reaction is favored. When the temperature is decreased, the exothermic reaction is favored. This is very important. For example, in this reaction mixture, they give delta H is minus 92 kilojoules. The value that they give for delta H is always for the forward reaction. So the forward reaction is exothermic. When the temperature was increased, that would increase the rate of the endothermic reaction. Therefore, it would increase the rate of the reverse reaction. Therefore, the equilibrium will shift to the right. And the new equilibrium will have less product than before. If the temperature was decreased, it would cause an increase in the rate of the exothermic reaction. Therefore, it would increase the rate of the forward reaction. The equilibrium will shift to the left, and when there is a new equilibrium, more product will be there than before. This is very important. Now, what about a catalyst? What does a catalyst do to your equilibrium? It would increase the rate of the forward reaction, and it would increase the rate of the reverse reaction. Therefore, the concentration of the reactants and the concentration of the products remain the same. Therefore, it would have no effect on the equilibrium position. A catalyst has no effect on the equilibrium position. Very important, the equilibrium constant. Only temperature affects the equilibrium constant.